So I posted the correction to lab report 2 in your folder. Okay, tomorrow is the third partial exam. Time flies very fast during the summer, right? And going back to the material that's going to be asked in the third exam. Copy this one as well. Right? Partial exam. Material for the exam. For exam 3. In this exam, we add the material that we covered in lab 1. Okay. Report of lab 3 is due today. Report of lab 4 is due tomorrow. Let's see, lab 4. We didn't do lab 4. Okay, so we are going to do lab 4 today. Let's take a look at the syllabus, right? Today is the 5th of July. I hope everybody had a pleasant holiday, 4th of July holiday. And we're still doing relativity. Lab 4 is going to be today, so it cannot be due tomorrow, right? It's due Monday. Monday, and that's going to be the 10th. Okay. Today we will do lab 4, right? Report for lab 4. Lab 4 report. For report is due on Monday. The situation here. Can you hear me, by the way? Just send me a text message so I know that you folks are there. I don't feel so lonely too. Okay. There are 9 students so far. So can you hear me, or just confirm that you can hear me so we can move forward? Yep. Okay. Thank you. So let's talk about the summary of relativistic Doppler effect. It's not, it's not that easy. Okay, you have to keep track of everything that's happening there. And again, it's deriving the relativistic Doppler effect is not that easy. Okay, that's because the ideas of relativity are very counterintuitive, even though they do happen. So I prepared this summary here of what you have to do, 10 different steps, right? So summary of the relativistic Doppler effect. First, we have referential A and B. So Remember that referential B is moving with respect to referential A. That's the velocity of B with respect to A. We have a light source with a given period frequency at the origin of referential A, right? At time t equal to 0 on both referentials, right? At time t equal to 0 on both referentials, their origin, both referential, their origins coincide. But also, at time t equal to 0, the light source emits its first wavefront. So the source is synchronized with the position of the two referentials. When the two referentials are collocated, the light source emits its first wavefront. We do something like that so we can calculate the problem in an easier way. Okay, and that's now when I start showing you the illustrations, right? We're gonna keep on going back and forth with these illustrations here. Here you go. That's time t equal to 0. The two referentials coincide. Referential A is the black one. Referential B is the red one. The light source is right here in the middle, and it generated its first wavefront. Okay. Now, a little bit later, referential B has moved this distance, VBA times T. And the first wavefront is ahead of referential B because the wavefront moves faster than the referential B. C is greater than VBA. Okay. At this instant of time as well, we have the second wavefront being emitted right there at referential A. Don't forget the source, the light source, is at rest with respect to referential A. And going back here, light source emitted first light wavefront, right? The first wavefront moves ahead of referential B because C is greater than VBA, because C is greater than VBA. At time T S sub A, okay? I put T S sub A here. Why did I do that? Is the period of the source with respect to referential A. Okay? That's what it's all about. Period of the source, S for source, with respect to referential A. The source emits another wavefront. And that's what that other drawing that you saw is all about. Right in here is this illustration here. This is just a small period of time after the emission, right? Here you go, the second wavefront propagating away from the source. Eventually, the second wavefront is going to catch up with with referential B, which is the spaceship. Okay, it is at this moment that an observer in referential B measures the period of this light source. The moment that the second wavefront reaches the second referential is going to be the period that B is going to measure the period of the wavefront. Okay. But we are in referential A, right? We are in referential A. At this instant of time, observer in A see the second wavefront passing by referential B. And that's where the complication arises, okay? That's where it's difficult to completely understand. Referential A already measured the period of the source, right? And now referential A is observing the moment, the instant of time that B is gonna measure the period of the source. Okay. And there is a relationship here, right? There is a relationship here, and the relationship is lambda plus VBAT is equal to CT, the speed of the first wave front. Okay, this T here and this T here is going to be the period that A measure when something like that happens. This period T, I rename it, in a different way. I remember I use this notation for the period of the source with respect to referential A, TSA, and then I use this notation here for the period of the source that A measures when the second wave catches up with referential B. Okay? That's a very important notation here. This is the instant of time in which the second wave front catches up with referential B. Okay, so that was TS prime A is all about. Is that T that you saw before? The second wave front catches up with referential B. TS prime A is the period that referential A measures when the second wave front catches up with B. But at this instant, at the same instant of time, right? The observing referential B is going to measure a different time period because of the time dilation. So this period that B observes is going to be related to this other period that A is observing. It has nothing to do with that. This period here has nothing to do with that. Those are three different periods. This is the period of the light source. This is the period that an observer in referential A see the second the second wavefront catching up with referential B, and this is the period of the source that an observer in B measures. Okay, and there is a relationship between those two periods. They are related according to the time dilation equation. And then what we do next? We relate this period here, right? Which is the period of the source with respect to A, with the frequency. So that's the frequency of the light that the observer in A measures. It's just the inverse of its respective period. And this here is the period of the source measured by B. And the inverse of the period. Let's put a prime here. I'm putting a prime because the source is not at rest with B, okay? But it's the same source. I'm just putting a prime here to let you know that the source is moving with respect to B. That's the notation. And then there is a relationship between those two, right? Determine, not find, but determine, right? Determine a relation between Fs prime B and FSA. Like that. So those were the steps that we followed. As you can see, it's not easy because there are several steps here that we have to worry about. Several steps that we have to worry about, okay? It's always good to have that accessible to you, even if you don't learn today, you know. In the future, you can refer to these notes, and in the future that when you look at this phenomenon over again, you can refer to this note, and that might be very helpful for you. Okay? In order to understand relativity, it's very important to get the proper notation. It is very important to get the proper notation. Okay? If you don't differentiate this period, and this period from each other, you will not be able to solve the problem. You will not be able to derive the problem that we proposed here. And then we get that relationship that you saw. Okay, and so the situation right now is this one in this chapter. Let's review, right? So what we propose to do. Okay, we did time dilation, and time dilation is closely in relativistic. We did time dilation and the relativistic Doppler effect, and relativistic Doppler effect is closely related to time dilation, right? The frequency is the inverse of time, right? That's why I'm saying that the relativistic Doppler effect is closely related to time dilation. And now we have to do Length contraction, which is another phenomenon that we get. Another counterintuitive result that we get from relativity. Okay. And by the way, length contraction can also be derived from time dilation. That's why I put them under this heading here of time dilation, okay? Relativistic Doppler effect is derived from the time dilation result. Length contraction too. So, and let's not forget, right? Time dilation is derived using the light clock, right? Relativistic Doppler effect is derived from the time dilation, Length contraction derived from time dilation as well. And again, we resort ourselves, again, we resort ourselves in order to derive length contraction, comma, we need again to resort to our thought experiment. Okay. And the thought experiment goes like that. Just like we did before, right? We have been using the thought experiment to derive all those relations that you see. Here. Like clock. Okay, the Doppler effect. Let's see if we have here. what I want, not this one. Okay, here you go. That's the one I want. Okay, so in order to visualize the length contraction, you have to, just like before, you have to create a referential A and a referential B. Here is my referential A. Right in here. Length contraction. So the story goes this way. The thought experiment goes along this way. And that's the one I want right in here. You have differential A, which, by the way, is in planet A. Okay? So we have this planet A, and far away from planet A, we have planet D. I put D instead of B. So let's keep it D. D is going to be for something else. So you have this length, this distance from this point to this point, right? From planet A to this planet D. And then that's the distance L. I put distance L. And then we have this spaceship that's passing by planet A. And this spaceship is attached, the rocket, right? It's attached to referential B. It's moving with this velocity, with this speed, VB with respect to A. Okay. Oh no, when whoever is here in planet A is seeing that the clock here on B is moving slowly. It's lower than his own clock, right? That's what this guy says. That's what this guy measured, okay? It's about measurement, right? It's not that this guy on B is feeling everything moving slowly. No, no, no. The observer in B is not seeing, that does not experience time flow slowly. He does not in his own referential. He doesn't do that. It is as though everything is running as normal, like he was on Earth. Okay. However, when this observer looks back at A, he sees exactly what A looks at see at B. He see that the clock in A is moving slower than his own clock. That's what we call symmetry. Because the two referentials are inertial, whatever one observes on B should also correspond to whatever B sees on A. And we have a very nice movie about that in that mechanical universe series. Right? So here go. Because of time time dilation. Okay, when this guy reaches here, this planet, remember, the whole trip he was moving with constant velocity, but in order to reach this planet here, he has to decelerate the ship, right? And land in the planet. The moment that he starts to decelerate in the ship, relativity, special relativity doesn't hold anymore. His referential is no longer inertial frame of reference, okay? But while he was moving with constant velocity until this point, relativity holds. So the moment that he lands here in this planet, decelerate and lands here in this planet, he discovered that he aged less than anybody else that was there on Earth, okay? So in order for that to happen, in order for that to be consistent, so basically what he's saying that his trip, the trip that he took from planet A to planet D, took a smaller amount of time according to his watch, according to his timepiece, okay? The timepiece that was left on Earth observed, measured this trip to be exactly what it's supposed to be, VBA, L divided by VBA, okay? But according to his clock, no, according to the clock of B, the time that took to go from A to D is less than the time that someone on Earth measured, okay? So how do you resolve this problem in terms of length contraction, okay? If the velocity has always been VBA, how can you have a smaller period of time from A to D, whereas this guy has a larger period of time? The explanation is in terms of length contraction, okay? That's what the explanation is all about. So when this guy is moving, okay, he sees this distance contracted because of his velocity, because of this distance, this fixed distance between those two planets. That's how the explanation goes, okay? So let's write it down. The steps are like the following. Okay. So you have to ask the following questions. You have to ask, consider a spaceship traveling from planet A to planet D. Okay, one, right? Step by step. Planet A is at rest with respect to our referential. To our referential and referential A, right? A. Planets A and D, okay, both of them, A, D, are at rest with respect to our referential and referential A. The spaceship moving at relativistic speed, right? At relativistic speed, dBA. dBA. dB with velocity of B with respect to A. The distance between planets A and D. Okay, let me put something else here in 3 before I forget, okay? So the spaceship is moving at a relativistic speed VBA, comma, and is attached to referential D, right? The distance between planet A and D is L, right? As measured by an observer in referential A. Okay. 5. So we can even put something like that, distance of D with respect to A, right? Distance of D with respect to referential A. Okay. When an observer, we or student, an observer in B experiences time dilation because his referential is moving with respect A and B. So okay, spaceship is moving at relative speed VA and attack the distance between planets is LD. I'm gonna do one more thing here. According to referential A, comma, this trip should last what? Should last, I'm gonna put here the formula. Okay. So here you go, T of the clock. Okay. TCA means, period measured by the clock in referential A. C means clock in referential A with respect to referential A, right? That's what it's all about. I am, so this trip should last what? L. Let's continue using the same notation of D with respect to A, right? Divided by B with respect to A. That's what we should measure. But I'm observing B experience time dilation because his referential is moving with respect to A and B. Okay. And how do you explain that? Experience time dilation with respect to A, right? With respect to A. Right? And how do you equate that in an equation? It's going to be something like that. There is a relationship between the clock left behind in A and the clock prime. Gotta do something else here. And the clock in referential B. The clock in referential B, I am denoting by C prime. There is a relationship and they are not equal. Okay. this time is dilated. So it has to be gamma, according to gamma. And let's not forget, gamma is what? 1 divided by square root 1 minus VBA square with respect to C square. Like that. So there's a relationship between those two periods. And now I want to know, I know that. I have already determined that. Non-parameters. LDA and VBA. And now I want to know that. I'm going to emphasize by bold-facing it. Okay. Good, 7. Okay, solving from the above, we determine the period that B measures with his own clock. Okay. From the above, we determine how long, right? How long the trip took for an observer in B. Yeah. So that's what we get here. Let's put it here, please. Oops. Like that. Okay. It goes here. Let's not forget this number is less than 1. Consequently, notice that this one is less than this other one. Because this term here is less than 1. A number that's less than 1 multiplied by another number is going to be less than this number. Okay? So that, and then how come this guy took less time to reach there if the speed that they measured is the same, right? Oh. Then you have to ask yourself, how come? How come? How come B is measuring a shorter amount of time if its speed is the same as measured in A and B, right? The answer is that B measures a shorter distance, L of D with respect to B. Okay? The distance of planet D with respect to referential B. Okay? And how do we get that? Okay, so we use the form. Don't forget, L, right, is L divided like that. L of D with respect to A divided by T of C with respect to A must be equal to V dA. Okay? Must be equal to VVA. In another way, right? You can rewrite that. That's very easy to see, right? Now we need another equation, but according to referential B. We need a similar equation, but according to referential B. Here you go. L of planet, the distance of planet D with respect to referential B must be given by the period that an observer in referential B measured with his own clock. And we are going to substitute that C prime like that, right? Like that. Note, see that this term is exactly equal to this term here, which, by the way, is equal to that, right? And let's continue. LDA goes here. And I'm going to prove to you that this length is shorter than this length. Okay? I'm going to prove to you that just by rewriting my equation. Okay, I'm going to rewrite it like that. Right? Hope, I guess you already have seen that, right? You have already noticed that. Don't forget, this is the square root of a number 1 minus a number that's less than 1. A positive number that's less than 1. 1 minus a positive number that's less than 1 is going to be less than 1. You take the square root, it's still going to be less than 1. So now I'm going to write it less than 1. Right? And now I use this inequation here, and I finally prove to you that the distance planet B as measured by someone in referential B is going to be less than the other lengths. Okay? Length contraction. This is length contraction. Okay, this is length contraction. We have a very nice video on the mechanical universe that discuss the same thing that we just did. Let's take a look at that. It's 8:45 now. Let's take a half hour. Let's watch that video for half an hour, right? And mechanical universe, length contraction. Lorentz transformation. Let's see. Which one did we watch? I believe we watched this one, right? Velocity and time. Let's take a look at this one. Let me see if that's the one. Let's see. I'm gonna fast forward here just to make sure that's the right one I want. Oh yeah, that's the one. Okay, good. Let's play it. I'm gonna skip that so it don't take too long here. Okay.
Let me start today by showing you a little demonstration before. I have here just a loop of wire connected to a galvanometer, which will tell us whether an electric current is running around in this loop. The laser beam, the spot on the screen, will move whenever an electric current runs in this loop. Now, all I have to do to make a current run through this wire is to take this ordinary bar magnet and move it into the loop, like that, or out of the loop, or for that matter, move the loop into the magnet and back like that. And that makes a current flow, and that was really one of the great discoveries of the 19th century.
That's electromagnetic induction, right? And by the way, Einstein, he figured out the relativity just by thinking in terms of this experiment. That's why he's doing this demonstration, okay? Just by having a reference over experiments that are very familiar, Einstein was able to perform to figure out relativity.
Well, by now we have mastered all of the formidable machinery of electricity and magnetism. We know all about how to describe such things. So let's describe how that experiment works. What happens is that a current flows through the wire. That means the electric charges inside of the wire are set into motion, which means something applied a force to them. Now we know what applies forces to electric charges. The force on the electric charge can either be equal to Q times an electric field if there's one present, that would make the charges move, or it could be equal to the charge Q times the velocity of the charge crossed into the magnetic field. That would also make the charge move. Okay.
Notice that he's doing a different notation for vector symbols, right? He's putting a tilde below the vector component. We usually use an arrow here at the top, but it's the same thing.
That's our equation. Let's see how we use it to describe the experiment that we just saw. There are two possibilities. One of them is this. The loop is held stationary, not moving, and I take the magnet and I move the magnet into the loop. That causes the current to flow. Now, in that case, the charges in the loop were not themselves in motion. So it can't have been the magnetic field of the bar magnet that made them move. But since they did move, there therefore was an electric field. And so we...
Did you get the idea? He's framing the whole idea of electromagnetic induction in terms of forces, but in terms of electric force, not a magnetic force. He's framing it in terms of an electric force. Let's continue with his explanation.
Conclude that a changing magnetic field moving the bar magnet created an electric field. And that, of course, was Faraday's great discovery of electromagnetic induction in the 19th century. And that's one explanation of that experiment. Now there's another completely different independent explanation, and that goes this way. Suppose instead I hold the bar magnet stationary and I move the loop. Now, of course, exactly the same thing happens. But in this case, we have no moving magnet, no changing magnetic field, but instead the charges in the loop are moving because I'm moving the whole loop.
Did you get that? Now we no longer, now we can interpret this force, this electromagnetic induction in terms not of the electric field, but in terms of the magnetic field, because your charges in the loop are now moving towards the bar magnet.
They have the velocity v, and this velocity crossed into the magnetic field of the bar magnet gives us a force which causes the current to flow. And that also describes perfectly well the experiment that we just saw. So those two different phenomena, that is to say, this loop stationary and magnet moving, and this magnet stationary and loop moving, are actually two completely distinct, independent phenomena that have completely different explanations.
Complete different, I would say even better, complete different interpretations, right? Completely different interpretations that still yield the same result. They still yield the same mathematical result.
When Albert Einstein saw that, he said, look, guys, you've just got to be kidding. Any yo-yo can see that those two are the same thing. So it was this simple little experiment that was really the starting point of the theory of relativity. Not
okay, that was the experiment that started relativity theory. Einstein started thinking in terms that how come you can have a magnetic field in one referential, but you have an electric field in another referential. That's what he's thinking. Okay, that's what he starts thinking about. How come?
the Michelson-Morley experiment, not some exotic experiment to detect the motion of the Earth through the ether, but this simple little phenomenon that, of course, everybody knew about, but which disturbed nobody else except Albert Einstein. And what disturbed Einstein was not that we had difficulty explaining these phenomena. This equation explains them perfectly in every case. What disturbed Albert Einstein was the lack in the inner perfection of the theory. And what he did in response was to produce a theory, the special theory of relativity, which had just that kind of inner perfection. And it's that theory that we're in the midst of studying right now.
It doesn't elaborate how Einstein went from this equation, right, to relativity theory, but that's how it started. He doesn't, however, remember, he did not elaborate. But that's exactly how it started. It has nothing to do with Michelson-Morley experiment. And it had to do with some other sort of experiment that Einstein was doing as well.
Historians recall the turn of this century as a revolution. No matter the field, from aviation to anthropology to art, departure from the norm was radical on all fronts. And the year 1905 stands as a crucial landmark. That's when Albert Einstein asked the world to get on the right track, to think for a moment about what a moment really is. Time is relative, he said, and a matter of simultaneous events. In Einstein's relativity, which is reality is a matter of simultaneity is a matter of opinion. Notice, for example, what happens when a light is switched on as Henry's train moves by. The light reaches the front and rear of the train at the same time. At least that's how Henry sees it. But consider an outsider's point of view. To Albert, at rest on the ground, the rear wall comes up to meet the light, and the front wall moves away from it. These two events don't look simultaneous at all, and that's the essence of the time problem. And in physics, the explanation of the problem starts with time dilation. Given the constancy of the speed of light, there's no doubt that a simple light clock in motion runs slow by a factor of gamma. But if a more conventional clock went along for the ride, would it slow down by the same amount? The answer is timing, because if only the light clock slows down, it might be possible to compare their times. Then if the times were the same, they would be at rest. But if the light clock were slower, that would be because they're in motion. But in motion with respect to what? The basic premise of relativity is that there can be no absolute motion and no absolute rest. And if those conditions don't exist, no experiment can possibly detect them. So if the theory of relativity is correct, every clock in the universe must behave exactly as a light clock does. And that's not just a discovery about clocks. That's a fact about the nature of time itself. Time dilation places the relationship between time and space in an entirely new light, which is exactly what was happening in art and literature in the early years of this century. In art as well as science, the idea of time and space was now far more than a passing fancy. Just as Einstein was trying to place everything in perspective, Virginia Woolf urged writers to move beyond the formal railway line of a sentence. And no writer innovated more with time and space than James Joyce. Like Einstein's world, writes critic Edmund Wilson, Joyce's world is always changing as it is perceived by different observers at different times. And so it went, around the clock, with scientists and artists, musicians and mathematicians, poets and philosophers. And Einstein's theory of relativity had gone at least as far as any creative imagination. On the track of relativity, velocity not only changes the nature of things, it changes the way things are perceived. That's because Einstein's relativity is a theory of motion as viewed by different observers. The theory applies everywhere, even Brooklyn, and includes all observers, even a good sport named Henry. They say Henry had one heck of a fastball. With it and a desire to pitch for the Brooklyn Dodgers, he was on his way to making the team. Some said Henry could fling baseball at nearly the speed of light. And from his point of view, it does look pretty fast. But from where his pal Albert stands, it looks even faster. Could the speed of the ball, added to the speed of the train, make Henry's pitch look even faster than the speed of light? Of course not. Because even on a train in spring training, nothing travels faster than the speed of light. So what's really happening here? Baseball statisticians work it out using a space-time diagram, where from Henry's point of view, the ball speeds one way and Albert speeds the other way. Since distance is one axis and time is the other, speed, say d prime, can be seen in the slope of each path. Just as the speed of light is given by the slope of its path. On this graph, light goes 1 unit of distance for each unit of time. So c equals 1. Meanwhile, Henry's pitch has a speed u sub x prime of 0.6. While Albert's going the other way.
We are not talking about slopes here, right? This slope would be, this slope here would be greater than 1. No, we are not talking about slope. We are talking about the speed, which is going to be delta x, which is displayed in x direction, and delta t.
Has a speed of minus 0.6. That's from Henry's point of view. On the other hand, as Albert sees things, the speed of light remains the same, but all other speeds are transformed because all slopes are measured on tilted axes. Of course, it's true that light still goes 1 unit of distance for each unit of time. So c is still equal to 1. But now, Henry's moving forward at a speed v equals 0.6. And the baseball speed, u sub x, measures 0.88. In the strange arithmetic of relativity, no matter how you look at it, when one speed is added to another, the result is always less than the speed of light. So, while Albert will surely agree that Henry throws one heck of a fastball, he can always throw a little light on that. And be sure it'll get there first.
Even along the direction of relative motion, components of velocity never add to a speed greater than the speed of light.
What you see here is obtained from Lorentz transformation, which is going to be our next topic. Okay?
And the velocity transformation does affect components perpendicular to the motion, because although distances remain the same, time changes from one frame to the other.
Even when the theory is as beautiful as Einstein's, it needs testing. And there is a test of relativity in a phenomenon called the decay of cosmic ray mu mesons.
Oh, by the way, this is the other experiment that I mentioned to you that proves relativity, that demonstrates the correctness of relativity. We had that case of the clock that installed in the airplanes, flown around the world, while another clock, exactly the same copy of the other clock, remains on the ground. Okay, and then we have this other experiment here. Let's perform at the top of a mountain to detect muon particles.
A quarter of a century ago, Dr. David Frisch of MIT and Dr. James Smith of the University of Illinois filmed a classic experiment proving the reality of the relativistic time dilation. They did it by measuring the flux through the atmosphere of a radioactive subatomic particle called the mu meson. Created at the top of the Earth's atmosphere by cosmic rays from outer space, mu meson zooms straight downward at nearly the speed of light. But laboratory experiments such as the one done here by Smith, show that new mesons disintegrate naturally after an average life of only 2/millionths of a second. That means that even going at near the speed of light, they shouldn't make it very far through the atmosphere before decaying. Or to put it differently, when Frisch and Smith observed 568 new mesons in their detector at the top of Mount Washington, they calculate that only 27 per hour ought to make it to the base of the mountain.
Okay, so we understand what's happening here. If there is no time dilation, they would expect only 27 mesons. New mesons would reach the bottom of the mountain. And yet,
but when they cart their equipment down to sea level, they find almost as many new mesons as they had at the top, 412 per hour. Of course, Frisch and Smith really aren't a bit surprised. The reason for the discrepancy is spelled out by the theory of relativity.
okay, so they measured at the top of the mountain and at the bottom of the mountain, okay? And they found almost the same number of new mesons at the bottom of the mountain. That's because of time dilation or length contraction. You can interpret that as a length contraction experiment as well.
Traveling at nearly the speed of light, the new meson's internal clock runs slow so that, as viewed from Earth, they take much longer on the average than 2/millionths of a second to disintegrate. Or, to put it differently, as viewed from the frame of reference of the new meson, the Earth's atmosphere, rushing upward at nearly the speed of light, is Lorentz contracted to such a degree that the particle can easily make it all the way to the ground in only 2/millionths of a second. A set of twins, born in virtually the same time and space, are on the surface very much alike. And yet, on the inside, may turn out as different as night and day. Being so different and so alike at the same time may be the ultimate paradox of identical twins. But in physics, the twins paradox conjures up another image. And like Einstein's theory, it begins with an extraordinary fact about clocks. No matter how long they've been around, no matter whether they tick-tock, chime, or say cuckoo, all clocks obey the rules of relativity. Naturally, these rules apply to the human clock. With a time-keeping device called metabolism, it starts running even before the moment of birth. And in a relatively predictable fashion, it keeps running to the end. But what would happen if the human clock were moving at nearly the speed of light? To find out, consider these identical twins, Albert and Henry. From the very outset, their biological clocks start out in perfect synchronization. Soon enough, however, the best laid plans of mother and father alike get out of sync. Instead of an orthodontist, Albert becomes a scientist. Henry chooses what's left of the wide open spaces, open space itself. Especially for identical twins, the first party is such sweet sorrow. Nonetheless, traveling at nearly the speed of light, Henry has no trouble leaving Albert behind. This is Henry's first long haul for his new boss, the Interstellar Baking Company. Destination, Zog, 10 light years away. Assignment, take a load of ordinary white bread and exchange it for Zoggy cakes, those delicious little buns that all the earthlings crave. But that's not what's so extraordinary. If Henry could compare his clock to Albert's clock, he would find Albert's clock running slow. If Albert could compare his clock to Henry's, he would find Henry's clock running slow.
Okay, do you see the symmetry here? There is a symmetry. Whatever Einstein see in the other clocks is exactly the same thing that Henry see in Einstein's clock. Provided they are moving apart, that is okay. But the moment that they get together, something must give.
And that spells paradox. How can each one be slower than the other? Fortunately, in the theory of relativity, there's no problem at all. For one thing, there won't really be a problem as long as the two of them are far apart. But what will happen when they're not far apart? Say, when they get back together for a family reunion. Again, in the theory of relativity, that's no problem. Brother Henry, at nearly the speed of light, will take about 10 years to reach Zog, 10 light years away. And then another decade to haul his buns back to Earth. To Albert, that's around 20 years. But to Henry, the twin who's actually en route, the situation seems different. Since it's Lorentz contracted, the distance to Zog seems like a milk run. A few hands of solitaire, 40 winks, and as far as Henry's concerned, it's hello to the bright lights of Zog City. Then, equally quick, because the distance is again Lorentz contracted, it's back to Earth just as fast. And so, when they do get to compare those biological clocks, while the result is amazing, there's no paradox at all. Henry, the twin who zoomed away and then came back, has only aged a couple of months. But Albert, the twin who never switched inertial frames, has aged 20 years. And so, even among relatives, time is relative.
Try to imagine, if you can, a completely empty universe, a universe with nothing whatsoever in it. In such a universe, it would make no sense at all to speak of time or space. The very concept would be meaningless. If there were one single object in the universe, it would still be true. Time and space would have no meaning at all. If there were two objects, then you could imagine saying, well, they're getting closer together or they're getting further apart. And then you're saying something about the flow of time and distances. If there were many, many objects in your universe, you might imagine using some of them to construct a device that could measure the flow of time or measure the distance between objects. But it would still make no sense at all in that universe to say one of these objects is at rest and only everything else is in motion. In such a universe, the simplest law of motion it would be possible to imagine is to say that each body continues in whatever state of motion it has until something interferes with it. And that, of course, is precisely the law of inertia. But that has to keep on making sense in a universe in which light can propagate through the void. Now, if light has some definite speed as observed from a particular frame of reference, then there is such a thing as a state of rest in that frame of reference. And the whole argument for the law of inertia collapses. Now, I don't know if there are any other logically consistent universes. But in our universe, that problem has been solved by making the speed of light the same to all observers, regardless of their state of motion. Knowing that, and only that, it's possible to deduce that if there are a pair of twins, and one of them stays behind on Earth, and the other one travels at high speed to a distant star, turns around and comes back, the traveling twin, when they get back together, will be younger than the one who stayed behind. I don't need to know anything about how clocks work, about quartz crystal oscillators, about human metabolism. All of those things are completely irrelevant. All I need to know is the principle of relativity and the constancy of the speed of light. And from that, I can deduce that the traveling twin will come back younger than the twin that was left behind. That is an absolutely breathtaking feat of pure human logic. That is the theory of relativity, and we'll get on with it next time.
Okay. Okay, so I was really impressed with this video when I watched it for the first time, because it really cleared up my mind about relativity when it shows this communication, right, between Einstein and Henry.
You could find Albert's clock running slow.
So that's critical that you understand that there is some symmetry. Here you go.
And if Albert could compare his clock,
There's a
Henry's,
symmetry in
he could find
relativity
Henry's
theory.
clock running slow.
If it works in one way, it should work the other way, provided the two referentials remain an inertial frame of reference. Once one is no longer an inertial frame of reference, then something else must give. And this something else is that is going to be the length. Would have to be the length contraction that Henry experienced during the trip. Okay. And any questions about that? What I want to do, I want to take attendance. Roster. July. Okay. July. Oh no, this one here. Let's start with Sydney. Are you there, Sydney? Okay, I'm gonna put star here on Sydney. Amy, are you there?
I'm here, Professor.
Thank you.
Oh,
Andy?
wait, sorry, that was for Sydney.
Ah, that was Sydney. Okay. What about Amy? Amy, no, Amy is not here. Andy? And are you? Okay, thank you, Andy. Alex Hernandez. Thank you. Sartak. Good, thank you. Basilio Lopez. Hello, Basilio.
Hello, good morning, Professor.
Morning. Okay, Jeshwan.
I'm here, Professor.
Thank you. Zaid. Zaid is not here. Sumana. Thank you. Alisa.
I'm here.
Okay. Karsika. I don't see Karsika here. Mary.
Here.
Thank you. Raymond. Ashley Tai.
Here.
Thank you. Kyriakos. I don't see Kyriakos here. Alexis Valley. Hello, Alexis, are you there? Okay, I'm gonna put a star here on Alexis, and we can. Yeah, 12 is Alexis. Okay, good. So it is almost 9:25. Notes. So break from 9:25 to AM, right? 9:40. So I see you in 15 minutes. Okay, 9:40 right now. And now let's go back, right? What we did so far. I want to keep on. I'm going to display the plan of this chapter over and over again for you, so you can follow what we're doing, the organization of this chapter. Relativity, postulates of relativity, light clock, time dilation, relativistic Doppler effect, and lens contraction. And again, I'm going to repeat, see that lens contraction is under time dilation. And the light clock and everything else is under light clock, right? What you're going to do now is the Lorentz transformation. A more powerful way of describing relativity. It's a more genetic treatment, okay? We finished the treatment using the light clock. That allows us to realize some interesting phenomena, some interesting effects that relativity detects. Next step is to start working with the Lorentz transformations, which is a more powerful tool. And it's not difficult to memorize the Lorentz transformations. It's not that difficult, provided you provided you remember the Galilean transformations. And we did that, right? So let's move. Here you go. That's what you have to have in mind here. Differential from A to B. We have this moving differential B position, and consider, a point P. I have already shown that to you before, right? Consider a point P, and we are making measurement of the point P from two different differentials. Okay, the position of point P with respect to A is XPA. The position of point P with respect to B is XPB. And then there is a relationship between those two transformations. I'm going to write that down for you. Using that very intuitive notation that I introduced to you. Okay, so here you go. Position, Galilean transformation. I'm gonna spell it out here. Galilean transformations. One would be the 1D, right? 1D Galilean transformation. Position of point P with respect to A is equal to position of point P with respect to B plus position of the origin of B with respect to referential A, which, by the way, can be written down as this one here. Velocity of B with respect to A times P. Okay. And the Lorentz transformation is for this set of equations, right? Is going to be what you see right here, but multiplied by the factor gamma. That's the only difference that you have for this specific transformation. And the gamma factor is multiplied again here. We can even put them side by side like a table. Things start to become a little bit more difficult when we go for other coordinates, okay? I'm gonna put here a table so you can compare them side by side. Three, 1, 2, 3, okay, like that. Galilean, let's see. Okay. Oh, okay. Galilean, Lorentz. I'm going to put this one on there. And I'm going to put this one there. Those two that I wrote down are exactly the same transformations, right? Just written a different way. I'm going to remove this. We don't need that, right? Let's leave it for now. Maybe we might need it. Position, right? Position. But we can do in another way too, right? We can do, you know, position of point A with or point P with respect to A. We can also write position of point P with respect, oh, not this one, with respect to B. The inverse, what I'm doing here is the inverse transformation. Like that. From B to A, right? From B to A, and from A to B. And what we do need here, just put the parentheses and the gamma. multiplicative factor, position of point P, right? Of point P. We can do even better than that. Let's try it. Lorentz. What I'm going to do here, I'm going to put another position of point P, right? From referential B to A, right? From B to A, B to A, from B to A, and then from A to B. Those are the highlight here. And we gotta go for the other one. It's not much different. Then you have seen that. And here now is going to be V of A with respect to B. And this one is equal to minus this one. And just like before, just add the gamma factor here. Just add the gamma factor there. But wait a minute. Time flows in a different way for each referential. Remember that? So this T here must be determined, this T, those two T here must be written in terms of the referential. That's the little trick here that Lorentz has prepared for us. And the way to do that, remember, we still want to have a transformation from B to A. So what I'm going to do, I'm going to just commute this here, and for a very good reason. For a very good reason. I'm going to put it here from B to A, right? And now do you see how we are doing that? Time of point P with respect to, oh no, I made it wrong here. Point P with respect to B. That's what you're supposed to have there. So is the clock on referential B. And here we do the same thing, but the inverse, right? I want to put in this format, I want to put T in front. So we have that neat format of the equations. PB, right? PB. PB here, PB here. Here's from A to B. And now we can start deriving other equations from this transformation. One of the things that we can do. One of the things that we can do, right? We can do is to consider the point P as being a photon of light. Okay, that's one of the things that we can do. And then, right, apply Einstein second postulate. Okay, which states that doesn't matter which referential we have, the speed of the light is always going to be the same. Okay, and what do we do? I'm going to hear this one here. See here. Yeah, okay, this one is correct. I'm gonna get this one here, this equation, and this equation. Two different transformations, right? From B to A and from A to B. We do know that if the point P is a photon of light, we can write that its position is going to be CT. But then this T is going to be the time of point P with respect to referential A. And we repeat it for the other equation with respect to referential B. The speeds here are the same, according to Einstein's second postulate. The next step, is to use the original transformations, to use the original transformations in the above table. Okay. So copy and paste. Right? Copy and paste. XPA is exactly what you have here. XPB is exactly what you have here. A little pause for you to absorb that. Make sense? Don't forget. I'm using Einstein's second postulate. Okay. Why am I doing that? Why am I doing that? I'm doing that because I want to have a relation between TPA and TPB. That's why. Okay, and that's exactly I'm gonna proceed. And how do you do that? I'm going to go XPB. We have this XPB here, right? And we have this XPB here. Okay, so I'm gonna even emphasize we have this XPB here. Oops. Emphasize that's this XPB that I want to use. I'm going to get rid of this term for now. Okay. So we can see clearly what we are doing. And I'm also going to use, it's not this one that I want, it's actually this one here. Okay. And then I'm going to highlight what we have. Let me unbold here. Note, see that if I replace this guy right here, both terms in the parentheses are going to have the TPB here, right? Now I'm going to highlight us. There's a reason for why we're doing that. Similarly, if I replace it here, I'm going to have this term there. So let's do it. XPB, CTPB, XPA, CTPA. And look what we're getting now. We're starting to get a transformation of time in terms of the from referential B to A and from referential A to B. Okay, and let's go to the next step here. TPB, 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 TPA, TPA, TPA. We're going to solve for TPA and TPB. We're going to have C downstairs here. We are going to have this one here. Don't forget, I want to and then we're going to do something else. We are going to get this term right in here. Okay. And we're going to get, that's how TPB relates to TPA, right? But there's another way too that we can relate. There's another equation that TPB can be related to. TPA goes right in here. The equation for TPB. Okay, now I This is a system of equations, okay? What I'm working here is in a system of equations. I'm gonna keep this until the very end. I'm going to start to simplify what I have here. Notice that I have C plus VAB and C plus VBA. Okay? Notice that. They are not the same terms. They are not the same terms. I can go the next step, and I'm going to keep on carrying this previous term. You know, I'm not going to use it right now. I'm not going to use this one right now, but I'm going to adjust this one. Remember that VBA is equal to minus VAB. Okay, and we are starting to get, I'm going to put out C squared here as well. We should have done before, right? And I'm going to put this term here, right here at this spot. Even better, I will, I'll put C squared in the previous one. Right? There's a reason why I'm doing that. And now, next step. Nice thing about computers is that I don't have to keep on writing this term over and over again, right? All I have to do is to copy and paste. I'm keeping this term there just so you don't forget that we had this term before. And now it's easy to rewrite this term that you see right here, right? I reduce that to the same speed. We had this speed v of b with respect to a, but v of b with respect to a is minus v of a with respect to b. And I'm going to put a notation here so you, in case you forget, right? V of a with respect to b is equal to minus v of b with respect to a. Like that. Even better, I meant the other one, right? I meant this equation here. It's the same thing, but it becomes more obvious when we write in this way. This VBA is replaced by minus VAB, which, by the way, ends up being the same as this term that you see right here. And look what a nice thing we get here. We're going to have a square, but it's going to be a negative here in front of the square. You know, this TPB cancels out this TPB. Okay, and what are you getting here? Here you go. I was able to cancel out, right? TPB with TPB. And look what we are getting. We're getting something that we already knew, but that's just a confirmation of something that we derived in a different way, right? Using the light clock. And by the way, what I'm doing here, let me explain what I meant by doing all of that. What I'm doing here, suppose I did not know what gamma is, but I did know that there was a transformation like that involves a term that involves gamma here. How do I find gamma? This is exactly what I'm doing, okay? So, next. C disappear, right? Becomes 1. I don't need this term. And now I can pass this term to the left side. Like that. Or, we can come up with the square root here. That's how we find gamma. We find gamma by setting up, that's how we find gamma, right? That is how we find gamma. By setting the transformation, by using, right? By using the second postulate in my supposed transformation. Okay. Now, let me go back here. I'll give you a little bit of break. Let's see. I want to give attendance here to Alexis. Here you go. Alexis, you're there, right?
Yes, I'm here.
Okay, thank you. And okay, so now we are going to find the relations, okay? The relation between, okay, the time coordinates. I'm calling the time coordinates because in relativity it's like that, right? Between TPA and TPB. But before we proceed, let me get my table right here. Okay. Here's my table. And now I'm going to put another, instead of position, time, right? Point P, let's say, do like that. From B to A, B to A, and from A to B. We have another student coming here. Galilean transformation, that's straightforward, right? There is no doubt that time doesn't change at all, whether it's in referential A or it is in referential B. So we can write that T of P with respect, right, to referential A is going to be T of P with respect to referential B. And if I'm going to here write this equation for from referential A to referential B, it's going to be something like that. B to A to B. What about here? How that is going to look like? Huh? What about here? How is that going to look like? We'll be able to find those relations just by using this original relation that you see here, that you saw here. Okay, so we start with our equations. I want this one here for the position, original equations for the position. Start with that. And how we are going to do that? Now we are going to replace this term right here. Okay? That's what they're going to do. XPB right here. And let's see if we can find a better relation now. Just a little pause, right? Let me emphasize here that XP from is a function of the following coordinates. XPB, I'm talking about just the coordinates. I don't consider the velocity coordinate. Okay? That's what we have. We have a functional relation here. What I want to do now, what do I want to do? I want to find from the above, come on, find the functional relation of TPA from B to A, right? And TPB. That's what we want. That's what I'm proposing here. From B to A and from A to B. Okay, so that's what I'm doing here. I substitute XPB right here. Okay. And when I do that, I will square my gamma term here and keep the same gamma term. XPA. And what we're going to do next, I'm going to collect the like terms that are the same, okay? I'm going to expand this equation that I have here. I'm going to do just for this one, you know. And then I'm going to pass. Oh, wait a minute. I don't want to do that yet. Okay, I multiply it, right? I multiply it and expand it. And expand, and now I'm going to pass this term here to the left side, so I can have this common term. Okay. Next step. Let's not forget that what this gamma square is. This gamma square is that term that you already know. 1 minus v of AB squared, of the velocity of A with respect to B squared. Do I have to do anything else? Okay. Let's keep on going here. Go. And now I can put this term here under the same. Let's see. Let's do better than that. I don't want to substitute for gamma yet. Okay, I should have put here the XPA in evidence. That's a better procedure. You know, a better mathematical procedure. And now I worry about the gamma square there. Now I worry about the gamma square. And the gamma square is going to be this inverse. And oh, I forgot something, right? You gotta put C square here. The gamma square has to have with the loss in terms of C square. And then there is something neat that happens when we have this type of relation. We can put everything under the same denominator, right? There you go. And when we put under the same denominator, the equation simplifies. Note C that this velocity can be either A with respect to B or B with respect to A. It doesn't matter. Why is that? Because we have this square here. Either way would work. Now let's go for the next step. 1 goes away. One more student coming. What time is that? 10:22. And I'm going to get rid of this parenthesis in the next step. I don't need this parenthesis anymore. And this negative sign is gonna go here. Okay. I will. You know, then I recognize that you see here is going to be gamma square again. We go back, we managed to make a simplification, right? And we go back to the notation. We initially spanned gamma square. We managed to make a simplification, and then we go back to the gamma square notation, which is going to be gamma here upstairs. What else can we do? Look what we're getting. We're getting XPA and TPA, the X coordinate and the T coordinate in referential A. And now I have my T coordinate in referential B. Okay. what we want to do, we want to write T of P in referential B with respect to the other coordinates. Let's do that. Okay, let's, I'm gonna pass whatever is in referential taking with respect to referential A to the left, and whatever is taken with respect to referential B in the right. Oh, we can do one more thing, right? I should have done before. I can cancel the gammas. Gamma, gamma, and gamma. Gamma, gamma, and gamma. Okay. Next step. What can we simplify here? Oh, take a look here. Here we have VA of B. Yeah, and VA of B, right? But wait a minute, we have a negative sign here on the left side. But watch out. We have B of A here, whereas I have BA of B here. So what I'm gonna do, I'm gonna cancel out the sign. In order to cancel out the sign, I'm going to rewrite VBA in terms of VAB. Okay. We do not want the time to be negative, right? Actually, the time is not negative. It's just that we didn't have a convenient notation. And now we're starting to get a better notation that's easier to recognize. And I am going to cancel out those terms. Almost there. Almost done. I will factor the gamma term. And we finally got our transformation from A to B. I even going to put in a different format because since we're solving for T, for the coordinate T, right? The coordinate time. I want to put the coordinate time in the referential way as being the first term. Then we can repeat that for TP of A, right? It's possible to do that as well. The procedure is similar, and just I'm gonna write the final result here for you. And I'm going to copy and paste that here, repeating for referential A, we get repeating the above. For referential A, we get I'm going to hit this guy here, right? And let's see how different it is. Don't forget, it's from B to A now, right? From B to A. If it's from B to A, so it's going to be velocity of B with respect to A. Kind of have the same notation, right? Whatever minus sign we have is going to depend which one is going to be positive, VB of A or VBA of B. See how symmetric the equations are? And I'm going to put them in my table now. Gamma, VB of A, C square X, P of B. P of B. Gamma. Over C squared. And now we can go back to our equation here in our table. Okay. That's TP of A. I'm gonna expand, give more space for my equations. And we get the other one, the other coordinate in the different, with respect to a different referential. Okay. Time coordinate, I like to call that time coordinate of point P. Put that in a better format. See, what is it? What is it? Layout, maybe? Yeah. No, not here. Sometimes they hide from you. I'm trying to combine those two cells in a single one. It is somewhere. I thought it was here. Navigation, one page, multiple pages. No. Review. No, you cannot. I'll leave this way. Time coordinate of point P. No, let's leave this way. The rest is gonna take too long. Let's see, maybe I merge. Here you go. All I have to do is right click. You know, it's not here. Let's see if it's easy to memorize that. No, I'm going to simplify this table now. Now I do not need this. I do not need this transformation. I do not need this transformation because I used it initially only as a reference to write my equations. Oops. Yeah, time coordinate. One like that. Merge cells. Erase it. Okay. And I can also merge cells here. Oh, good. Okay. I think it's better to put the notation in the following format, like that. Okay. I'm going to, why is that? Why am I doing that? here I'm lining up the time coordinate with the x coordinate, right? And whatever is dependent on the velocity, I also line up here. For the x coordinate, we could also divide by c squared. Can do it this way as well. Okay. Those are the transformations for time. Okay. And what else? Position of point P. What else am I missing here? Right? I'm missing the other coordinates here. Right? I put x. I gotta put y and z as well. That's the only thing that we're missing. And I'm going to from B to A. Let's see, we need more, right? Okay, we need one more. Merge cell from B to A, from A to B, from A to B. So what I have to do? I want you to point out that any changes in the coordinates is affected only in the direction of motion from B, wait a minute, from B to A, yeah, okay, from A to B, B to A to B, good, I have it. So if the velocity is perpendicular to the y and z axis, there is no effect on those coordinates. That's why I'm writing here. And if in the Galilean transformation, it looks just like that, in the Lorentz transformation, it's going to look just like that too. The only difference is going to be in the direction of motion. Okay. I'm even going to do the following too. I'm going to here write this table in a different way. I'm going to here organize this table in a different way. I'm going to do the following. A to B, X, Y, and Z. Like that. From B to A, delete, delete. You sell that. A to B, A to B. And I can even go further. What I'm going to do, I'm going to put all the coordinates of point P. Let it be spatial or temporal. B to A. B to A. And this can disappear as well. Delete cell. Delete cells. Lift up. Good. I'm going to delete this one as well. Shift. Don't do anything. Well, we leave this way. Yeah, it's not behaving the way I wanted. But and now what else can I do? I can merge those cells and make it simple. Merge those cells. Make it simple. Okay. Merge cells. Merge cells. And organize it. And let's see how we can. Let's come up with some examples, right? So you can understand how those equations can be applied. Yeah, that's the best I can do. Okay, so Galilean and Lorentz. From B to A, from A to B. 1, 2, 3, 4. 1, 2, 3, 4. X, Y, Z, and T. What time is that? Any questions about that? Let's see when we. Yeah, it's already time for our break, right? (9:40), yeah. 9:40, yeah, that's right. It's time for our break. We have how many students? We have 13 here. Looks like we have one more. Yeah, who else came in? Let's see. Aini, are you there? No. Zaid. Oh, Zaid's here, right? Hi, Zaid. Say there, you're there. Okay, good. Thank you. 10:42, and now we have 13. Good. Now, just remember that. Wait, yeah.
Oh, I'm here too.
Who is that?
Karthika.
Kartika. Let's see. Kartika. Okay. Thank you. So someone else left. Okay, I'm not gonna struggle with that. But so now you have the equations that describe exactly that animation that you saw in the mechanical universe. Clocks, the clocks that Einstein see in Henry's referential. Henry's referential has several clocks, right? They measure differently according to Einstein. Why? Because the time from one referential to the other, here is Einstein's referential, right? Depends on the position of the clock. P in this case is going to be the clock. Depending on the position of the clock, each clock is going to indicate a different instant of time. Do you remember that? And in case you don't remember, let's go back there. Let's go back. Let's see if I can find that for you. It's going to be one of those drawings that you saw. Drawings moving referential. You must have several clocks. If it's not this one, it's going to be the other. Yeah, this is just the velocity. Okay, it must be in the other. So I cannot find here. We still have how many minutes? We still have one more minute. Let's look for it in case that you didn't notice it before. 40, this one is 43. I want the 42. Episode 42. Mechanical Universe. Episode 42. That's the one. Okay, so here we go. It's one of these illustrations. Okay. Not exactly this one. Length contraction. Not this one. Oh, here you go. It's this one that I want. Okay. Let's rewind a little bit. Okay.
Lorentz found that for the new relativity, this must be multiplied by the factor gamma. That's the equation along the direction of motion. In directions perpendicular to the motion, distances are the same in both frames.
Okay, here you go. See, Lorentz has multiple clocks and they are all synchronized, right? They're synchronized, but they are at different positions. Because those are the proper, we call it the proper referential of the clocks. They are all synchronized. Proper referential, remember that, the referential in which the clock is at rest.
Although clocks can be synchronized in any one frame.
Oh, now they are not synchronized because the clocks here are not in the proper referential. It is being looked from Einstein's referential. And it has everything to do with that dependence on the x position of the point or the clock that's being analyzed. Oh, what happened here?
The readings in another
Okay,
frame
so
depend on
1046.
where they are.
That's what I want to show you. And here you go. That's the equation that we just derived. In a slightly different format. We have a negative sign here because he's not using the same notation that I am, but it's exactly the same equation. See, he's using a prime here. Prime is the other referential, okay? T prime is T for each of those clocks. What he's calling T prime is in reality T of P with respect to A. Okay, T of P is those guys here. T minus the x over c squared. We got exactly the same thing. I don't like this notation because it's difficult to remember what is what. If you put the subscript in there, the notation becomes more intuitive to organize. Okay. And that's what I wanted to do it. And we're going to continue with those derivations. And also I want to prepare an example for you, so you can have a better understanding on how to use these equations. Okay, break from let's go 1050, right? A little bit longer. 1050 to 11:05 a.m. Any questions before I go? Okay, so I see you in 15 minutes. I'm back here, folks. 11:09, and we're gonna have our lunch break soon. Okay, let's go for an example. Example using Lorentz transformations. Okay. You're at rest with respect to the ground. Okay. You see a supersonic airplane flying at 1 kilometer per second. Okay, 1 kilometer per second. Along the x-axis, right? Along positive x-axis. Constant velocity. Both you and the pilot observed a second supersonic airplane moving at 0.4 kilometers per second. By the way, this one here is Mach 3. This one here is Mach 1. And by the way, both you observe a second supersonic airplane. Okay? The speed of the second plane is 0.1, but I always have to state with respect to the ground. Okay? Along the positive direction as well. Positive x-axis. I always have to specify what is the reference, right? What's this? The velocity with respect to what reference? Is the velocity with respect to the plane, or is the velocity with respect to you, right? So use the Lorentz transformations. We just derived, right? We just obtained, let's not say derived, let's say we just obtained to determine the velocity of the second plane with respect to the first plane. Okay? Think about that. Let's see if I have an illustration for you. I don't think I do. Yeah, unfortunately, I don't. Maybe I have elsewhere. It's always good to picture it in terms. It's always good to picture a problem, right? Yeah, okay. I'm gonna take advantage of this illustration here, okay? So the situation is like that. Point P is the second airplane. And I'm going to put this plane right here. But referential B is the first plane. Oh, I don't want that. I want the other one. I want this one here. Nope, not this one. This is what I want. Yeah. Example. Here you go. Referential A is you, right? You. Referential B, first plane. First plane. And point P, I'm going to put it elsewhere. Second plane. second plane like that. And I need also the vector velocity. Velocity of point P with respect to A. Okay? That's the point P. That's how we should illustrate the problem. And by the way, here should be from B to A, right? Not on A to B, it's from B to A for this specific slide. Now that we have a picture of the problem, right? We can start solving it. The first step is to identify which is which with respect to our equations, right? U, differential A. Plane, first plane. Differential B. And second plane, point P. We have our equations. Everything is moving with respect. I'm gonna copy everything here. Everything is moving along the x-axis. Okay, so we don't need these two here. We do not need those two either. Delete rows. But we do not have an equation for the velocity, okay? We don't have an equation for the velocity. But we can find the equation for the velocity using those equations that you see here. It's possible to do that. Let's do that. Okay? Here you go. I'm going to start with this one here. And this one here. The first thing that you have to know is that the velocity of point P with respect to referential A is going to be the derivative of the position of point P with respect to A of XPA, right? With respect to time, right? Something like that. Okay. That's how we start solving the problem. Not only we start solving the problem, but we also start obtaining other equations, the equations for the velocity, for the relativistic case. Okay. So we are going to go and write here XPA. XPA goes here. And we are but wait a minute. This gamma here is not a function of time, so you can take it out. And let's go take a look at gamma, which is, by the way, square root 1 minus b with respect to a square divided by c square, right? That's what this gamma is all about. Okay, like that. But wait a minute, this guy here, VB of A, okay, VB with respect to A is only 1 kilometer per second. So let's put that here. Whereas per second, and we're going to square it. Whereas the other term downstairs is going to be much larger. It's going to be 300,000 kilometers per second. Squared. What does it mean? It means that this term that you see here is going to be approximately 1. Okay? Whether it's for this equation or this equation. Okay, so let's rewrite that. For our specific case, it's going to be approximately this. Which, by the way, is not the relativistic case. But then we can do something else too. This term, VB of A, is much smaller than c squared. So we can make a second approximation. We can make a second approximation in this second equation. Right? And then I'm just going to repeat what I have for the first equation. Okay, and this guy is gonna go like that. And we can continue our derivation. What? I'll write it here. So my VPA now becomes, first is this term here. I'm gonna put a parenthesis. Right? First is this term here. And oh, don't forget there's an approximation. This term is approximately equal to the other. We don't come in. And we can break it down into two different terms. Okay, this one here. This derivative, we know how to solve it. All right, is a constant. V with respect to A is a constant. And then this other derivative here is going to be 1. And we get what we were supposed to get for the Galilean transformation. This term here is going to be V of P with respect to B, right? Plus G of B with respect to A. We didn't finish the problem yet. What do we want? We want the velocity of P with respect to B. Okay, that's what we want, this term right here. And can just invert the equation and get, I'm gonna put this one on the left side. Okay. Like that. This one is 0.4, right? And the other one is 1. So it's going to be, so P of B is catching up with the other airplane. 0.4 kilometers per second. The other one is 1 kilometer per second. And we get minus 0.6 kilometers per second. That's what we get. 11:28. We started our 11:05, right? Ah. Let's do something. Let's see what I'm gonna do now. To the velocity transformation equation, okay? The velocity transformation equation is just start to do in this example. You can do velocity transformation equations. Transformation equations. Since we started to somewhat look at that, right? Let's go into this one. And in order to do the velocity transformation equation, we gotta go back to what we had here before. Okay. But I still going to let us start with I need that equation here. Let's finish what we start doing in that example, right? Let's finish. Let's find out what's that? Okay. And I can even put my differential sign right in here. And I'm gonna copy that as well. And another differential sign. Whoops. This gamma goes outside, right? Because it's a constant. Right from the bat, we can see that the gamma can cancel. This gamma cancels with this one. Okay, that's how we determine from B to A, the velocity from B to A, right? But then we can also find out what's the transformation from A to B. Okay, from A to B. Let's go from A to B. All I have to do is to change the subscript here. That's how convenient this notation ends up being. And here we have to change AB, right? AB here upstairs, and AB here downstairs, upstairs and downstairs, like that. This is this. Let's make sure it is what it is. Yeah. And this is this. Okay. The gamma cancels out. And then we can distribute the differential with the two terms. That differential here, and this differential here as well. These terms I will replace right here. In the next step, VAB is constant. Remember, this is special relativity. In special relativity, the differential cannot be accelerated, so we can take it out from the total derivative parenthesis. And then we try to figure out how to move forward, right? There is a nice technique that we can do. One way to do it is to put DTA in evidence. DTPA in evidence. If I put DTPA in evidence, I have to divide the XPA by DTPA. And I do the same here. Okay. Looks like I'm doing too much here. Let's see. Let me go back here. Yeah, okay. I'm okay. I'm just putting DTPA in evidence. Good. So here you go. That's okay. We're in good shape here. And look what nice. Look at the nice thing that happens. The DTPA cancel out the DTPA. And now I can get rid of the parentheses, the TPA upstairs, the TPA downstairs, and then we can start to recognize what we have upstairs and downstairs. What you have right in here is the velocity of the point P with respect to referential A. What you have right here again is the velocity of point P with respect to referential A. Okay? And by the way, I need to emphasize that this is the x component of the velocity of the point P. The x component. That's why I should put the x in there in the notation. Okay? X component of the point. Here you go. X component of the velocity of the point. This is the velocity of the referential. So if I were to write that, I'm going to emphasize that this is the velocity of the point P with respect to referential B, but it is the x component. Like that. And now we have this relationship. Okay? Note that if velocity of the referential A with respect, if those two velocities are not relativistic, right? This term disappears. And we go back to the Newtonian case or the Galilean case. PAAB, PB, PAAB, right? Let's take a look at the book notation. Oh, I don't have the book notation here. That's okay. Okay, I don't have the book notation. But book notation is slightly different. Here, my notation has more information than the books. Now we can do the y component as well. We can do the y component, okay? Instead of gonna be a little bit easier because the y component, you know, doesn't have that relativistic term, right? Doesn't have the relativistic term. And next one. I'm going to see DTPA, okay. Okay, the XP, the only thing that changes is this term here. YPA. And by the way, we have the gamma, right? Because this term here doesn't have the gamma. Okay, I gotta make sure I put the gamma right in here. Oh, not this one. Gamma. Gamma. In my next step, now it's better to get rid of what I have from the previous one. Otherwise, I can get confused, right? What I have to do next is put the TPA in evidence. And when I put the TPA in evidence, I must divide this term. And let's not forget that this term is constant. For this reason, it can be outside the derivative. And we no longer need the parentheses. Okay, that's what we get. We're not done yet. Since we are going from A to B, right? We can change this notation. VB to A. VB with respect to A. A to B. This should be VP with respect to B. Let's not forget that is the Y component of the velocity. And now we know what this term is, right? It's going to be V, the X component of P with respect to referential A. But wait a minute, we want to change from A to B, right? Consequently, this velocity here should be BA and not AB. When we move to BA, we add a negative sign here. Oh, and finally, hey, we have this guy here. We gotta put that upstairs, by the way. Like that. One more step. The velocity of point P with respect to referential A. Oh, and let's not forget is the Y component of the velocity. Here's Y component, here's the X component. So the particle can have components, right, of the velocity. And what is the Galilean transformation? The Galilean transformation, in the Galilean transformation, this term goes to 0 and this term goes to 1. So we end up with this term here. We do the same for the Z component of the velocity. I'm not going to derive because you already must have noticed the procedure, right? The Z component of the velocity of the Z component of P with respect to referential B is going to be the ZPA the XPA. Yeah, the same. The same thing that we have downstairs for VY, right? We're gonna put them side by side, like that. And let me get the other one too, right? You know, this one here. Let's see if we can figure anything easy to remember here in those equations. Oh, I didn't do that. See, we can change from A to B, right? We have to change the notation. We change the notation for X, we get a negative. Note that every term downstairs for X, Y, and Z are exactly the same, right? Note that. With the exception of the gamma term for the Y component and the Z component. But upstairs, we must have the term of the Galilean transformation. Whereas here, we must have just the Y component of the velocity of point P with respect to A. And since we are going from A to B, right? Again, we have to put a negative sign there. There's nothing wrong about that notation that I put before. There's nothing wrong about the equation that I had before. But if we want to be consistent about the transformation from one referential to another, we should write down in this term. Non-relativistic term, this disappear, right? One, let's do it. Non-relativistic term, non-relativistic case, relativistic case, much greater than VBA. Relativistic case. All those three velocities. This disappear, right? And we are left with the equation that you already know from physics 37. This becomes 1, and this disappear. This become 1, 1, oh. And this term disappear. Like that. Now we can do an actual example that involves relativity. Let's go until 12 noon, right? And then we have our half an hour break, and then we do the lab. Let's take a look at the illustration here. Yeah, that's the one I want. Okay, so here you go. Referential A. Referential A is the observer. Particle, point P, moving along the x-axis with half the speed of the light. This particle P can be an electron, can be some nuclear particles. We managed to accelerate those things very close to the speed of the light. When the Chernobyl power plant, nuclear power plant in Ukraine, by the way, blew up, okay, we had uranium atoms being propelled at relativistic speeds, close to the velocity of the light. And they would leave a trail, a bluish trail behind them, because the energy was so large that those particles were able to give energy to the oxygen and nitrogen of the atmosphere and make them glow, okay? So we can have a situation like that in which particles move close to the speed of the light, but it has to be nuclear particles, microscopic particles. And it's interesting, right, that we had the situation that in Ukraine several years ago, it was back in the 80s, and now the Russians are threatening, giving the impression, right, that they're going to blow up the other nuclear power plant in Ukraine, which is the largest one in Europe. Let's hope nothing like that come to fruition, right? Go, and now we have referential B with a second observer. Referential B is moving along the x direction at 8/10 the speed of light. And I have the velocity of P with respect to A. I want to find the velocity of P with respect to B. Okay? So we can write down okay, consider example. Referential A is at rest with respect to U. Okay. A particle P is moving along the positive direction of the x-axis with a speed, with half the speed of the light, with the speed of 0.5 c. A second referential B is moving along the positive direction of the x-axis with a speed of 0.8 c with respect to A. Point 5 with respect to A. Okay. Find the velocity of point P with respect to B. With respect to referential B. Okay. If you were to do that, let's go back to the drawing, right? According to Galilean transformation, we would think that this particle is moving at minus 3c with respect to B, right? We would think that. But Lorentz transformation says something else. Okay, so let's go there. According to the Galilean transformation, 11:55. Let's see if we go until 12 noon. Vp with respect to B is going to be Vp with respect to A plus V of A with respect to B. Okay. But wait a minute, we do not have v of a with respect to b. We have v of b with respect to a. So this equation must change. And now you can g of p with respect to a is again 0.5. 0.5c. G of b with respect to a is 0.8c. Okay. -3. -3. Like that. But we don't want the Galilean transformation. Those are relativistic speeds. We want something like that. X, Y, and Z. We are going to get rid of this one and this one because the particle P has no component along the Y and Z axis, right? There you go. So I'm gonna put 0 and 0. Vy of P with respect to A is equal to Vz of P with respect to A, which is equal to 0. But we are left with this one here. V of P with respect to A is 0.5c. V of B with respect to A is 0.8c, velocity of light. The velocity of B with respect to A is going to be 0.8c. And the velocity of the point particle with respect to A is going to be 0.5c. Here becomes -3, minus 0.3. C and C cancels out. 0.4, right? Like that. Like that. And then what we get? It's a big difference. Because we're using relativistic speeds, it's not going to be minus 0.3, it's going to be minus 0.5. So it appears to the guy in referential B that the point particle is moving out half the speed of light in his direction. Galilean transformation according to the Lorentz transformation. Lorentz transformation. All right, like that. What time is that? 11:59, and we can have our break now, lunch break, and return. Break from 12 noon to 12:30 p.m. Okay. Any questions? Okay, I see you in half an hour. Okay, so 12:30 p.m. And let's get ready for. Oh, by the way, did you get your correction there in the? Remember, I uploaded the correction to report to lab to the report of lab 2. Okay, make sure you have it there. And I'll be correcting the report of lab 3 soon. What they're going to do now is lab 4, right? And let's take a look here at our schedule. Standing wave 2. Let's do it. Okay, as we get closer and closer to the finals, okay, I won't be able to give you much of many days in advance, okay, so for the other reports. So we will need to speed up the turning. Let's see, this one I can leave it for, yeah, for Monday. But the others, we have to do all those 3, okay? Let's do the following. You turn in on the final, okay? Let's do this way. Okay, I'm gonna write it down here. Let's put this way. 1, like lab report 4. Report for lab 4, right? Report for lab 4 to July 10th, 23. And then I'm gonna do it like that. 2, 2, and 2. Reports for labs 5, 6, and 7 to 13th, the date of the final exam, okay? Can do it this way. So we can finish everything on time here. And I'm gonna get the spreadsheet for you. For this report is very similar. This experiment is very similar to the other one that we did. Google Drive. Well, I don't know what takes me there. Huh. Let's see. Okay, good. Works. We keep on changing the interface, right? Oh, that's number 5. Is that right? Let's see if that's the one. No, that's not the one. Not the one I want. Let's do this one. Let's see. Yeah, that's the one. I'm gonna change their numbers because it had a different number in the past. That's gonna be number 4. Let's see. One is asking a question. If you happen to do attendance in the next minute, I'm not going to the bathroom. Okay. Okay, that's going to be 4. Uh-oh. 4, Someone else is coming. Oh. Oh, group one. Let me make sure everything is right here before I distribute those spreadsheets. Okay. Okay, so let's move. Okay, group one, spreadsheet. Group two, spreadsheet. Group three, spreadsheet. Group four, group five. Make sure you have the spreadsheet there. Okay. That's the one here. We can no. So we are clear here. Report for lab 4 due on Monday. Report for lab 6, 5, 6, and 7 gonna be due the final exam. Okay, the day of the final exam. Gonna be a little bit tight, but you can do it. I'll help you out. Let's take a look at how we do that. Let's see, P39. Let me get it. It's not much different than the other one. The only difference, let's see if it's here. The only difference is how we perform the experiment. Okay, no, not this one. No, it's not here. I'm looking for, let me pause the recording. Just like before, we have one end let's see, one end of the string attached to a vibrator, to a vibration source. Okay, and the string is attached to the other end to a mass. And depending on certain parameters, right? It can be the mass hanging here, it can be the length of the string, it can be the frequency of the device. You can find some specific points where you are going to have a standing wave. And what's the difference between this activity and the previous one? We go back right here. Uploaded your data into your folder before load the Special Relativity. Okay, that should be okay. You don't need that. Okay, that's not what it is. Okay, so here you go. Tension versus vibrating lengths. That's what we are doing this time. What we did last time. This time we are going to vary the lengths of the string. And what did we do last time? Let's take a look there. Okay. Lab 3. Oh, where? Oh, here you go. That's the drawing, right? That's the drawing I was looking for. Okay, in the previous one, it was the tension versus the mode number. Okay. So what we are doing, we are choosing which mode we are exciting. Fundamental mode, second harmonic, third harmonic, fourth harmonic, and so on. And then we would look for the tension in the string that would produce those harmonics. That's what we did last time. This time, what we want to do is we want to vary the lengths of the string and find out what would be the mass required, what would be the tension required to achieve resonance for a specific length. Okay, that's what the difference. Okay, in the previous lab, let's write it down. In the previous lab, I'm not going to call lab, I'm going to call activity. In the previous activity, we varied the tension in the string to produce different modes of vibration. Fundamental, first harmonic, second harmonic, etc. In this activity, we will adjust the length of the string and find the tension to generate a specific mode of vibration. Okay? And then what are you going to do? You're going to plot graph mg, right? Plot the graph mg in the y-axis and L prime square on the x-axis. Don't forget that L prime is the length, the vibrating length, the length that's vibrating. Log the slope in the last table, right? Working on the units, work on the significant figure, fill up the table. And we go ahead and just do the derivation like we did before. Let's take a look here. Oh, Here you go. That's the frequency, okay? That's the speed of a wave, of a light wave, and that's the speed of a wave in a string. We're gonna work on this formula here. Okay, and here you go. We have that V is lambda over T with square root of mg. L, the L comes from the linear mass density. And out of the string, we know, okay, we know that the fundamental mode has this relation with the wavelengths, right? For 2 lobes of vibration is 2 lambda over 2, for 3 lobes of vibration, and so on, right? For n lobes of vibration, lambda is 2L prime over n. So what do? We go ahead, replace lambda for n equal to 1 here. And we're using n equal to 1. Let's take a look there at the raw data. Good. Now look at this one. I'm going to do the attendance very soon. So here you go. Take a look at the table, right? Here's the length of the string. Here's the mass of the string. This mass, we use a scale with 5 decimal places to determine the mass of the string and the complete length of the string. And we're going to be using n of vibration for this specific one, 2 modes of vibration, the second harmonic, 2 lobes of vibration. The frequency is going to be the same as the one that we used before. The device that we used before, it was the vibrating fork. What you see right in here is the mass divided by the length of the string, so you can have the linear mass density. And G is 9.8, right? Don't forget to put the units here. And you have all the data. Let's go back to that note. Okay, what I have to do here? Let's see, for 2 modes of vibration, it's 2 lambda over 2, right? So 2 lambda over 2 is going to be L prime equal to lambda. So I'm replacing lambda with L prime right in here. If you want to get a linear equation, linear relation for mg in terms of L prime, we have to square both sides. And that's what I did. The square root becomes mg L over m, and the right side becomes the square of everything here, 2L prime over nf. N is equal to 1, or n is equal to 2, sorry. N is equal to 2. So here's my y, here's my m over L, which is the linear mass density. And we have to square everything that you see here. That's what we end up having here, 4f squared n squared. What you see right here is the linear mass density, and I'm going to write here mu, like that. Everything is going to be black. Everything is going to be black. We're going to plot that along the y-axis. We're going to plot this one along the x-axis. It's going to be L prime squared. And you're supposed to get a straight line, and your slope is supposed to be given by this value. And here in this case is 2, right? So when we square the 2, the 2 cancel with the 4 upstairs, and that what ends up being your final equation. Okay. Make sure that you are using n equal to 2 there in your report. It's very possible that you'd have different n's from one group to another one. Okay. If you have n different of 2, please let me know. And going back here to the spreadsheet. Okay, so here's my linear mass density. So we start in this specific case. Let's say we start with half meter. We start with half meter of length of vibration string, right? Get half meter, but the string is longer because you still have to hang from the mass. You have to attach the mass at the end of the string, right? But what is vibrating is, for instance, half meter, and then you get this type, this mass to generate your second harmonic. Okay. So that would be the tension required to generate a second harmonic. You can, because it's a second harmonic, the wavelength is supposed to be equal to the vibrating length of the string. And what you end up having here is L prime square. What's going to go in your x-axis? What are the data? What is the data and what is the results, right? This is data. This is data, raw data. You're measuring that. This is raw data. You are given this value. We can observe how many nodes are vibrating. Here is data, 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 data. Here is also data because the students are measuring the wavelengths. Everything else is this one is considered data as well because we measured using a stroboscope. Everything else is considered a result. This is a result. These are results from a previous experiment in physics 37. Result, result, result. Okay. And we're going to plot those 2 results here. mg versus L prime square. Let's see if we get a straight line. Go. Trend line, display equation chart, R square. Yeah, I'm getting a pretty good straight line here. 28786. But it's a little bit off, right? They slope a little 2.8786. Let's see how much percent, 13% difference. Yeah, they're a little bit off there. Sometimes we get this type of result, okay? Let's see how good you get. And I want to do the following. I want to take attendance right now. Don't forget, you must be present to get credit for the lab activity. You have 15 students. That's good. Oh, today is the 5th. Yesterday was the 4th of July. Tomorrow, tomorrow is going to be the exam. Let's see. Oh. Yeah, contents. Insert. Good, finally. Took me some time. We're gonna need another one here too. That's gonna be the 6th meeting. Meeting number 6. Amy, are you there? Amy, huh? I don't see Amy here. Alisa?
Here.
Thank you, Alisa. Ashley? Okay, Ashley is here. Startup. I can see. Thank you. Ashley, yeah, yeah, I gave you attendance, Ashley. Here you go, Ashley time. Now, what about startup? Okay, good. Thank you, startup. Mary. Thank you, Mary. Raymond. Thank you, Raymond. Basilio. Basilio there. Jeshwan. Hello, Jeshwan. Okay, I'm gonna put a star here in Jeshwan. I can see here. Zaid. Thank you, Zaid. Karsika. Yeah, I can hear you, Karsika. If you can type there in the chat window, I would appreciate. Or raise your hand. Right. Karsika, I'm gonna put a star here. Sydney. Hello, Sydney. Okay, thank you. Sumana. Hello, Sumana. Oh, thank you. Kirakus. Good. Andy. Andy Heath. Next is Alex Hernandez. Hello, Alex. Are you there? Thank you. And Alexis Madrigal Valle.
Here.
Thank you, Alexis. And let's make sure everything 12, 13, 14, 15. Okay, so there are two students I didn't hear from them. Joshua, are you there? And Karsika. Okay, so good, 6. I want to make sure that you download it, right? I have a little birdie here tweeting in my window. You hear him? Tweety bird. So let's go for our, so can you picture how we perform this experiment? So all you have to do is change the length, the vibrating length of the string. Half meter, in this case, it was half meter, increased to 75, 1 meter, 125, 1.5, 175. And for each of those lengths, we had to find out what was the mass required to generate 2 lobes, the second harmonic of vibration. We're not changing the frequency. The frequency remains at 52 hertz, more or less. There at the Lake Harbor, we have this source of vibration, and this source of vibration cannot be adjusted. It's a pity, because it's much nicer to do the experiment, to be able to do the experiment by varying the frequency. Okay, but not in this one. And then at the end, we plot mg in the y-axis, L prime square in the x-axis. Let's see what I already did that, right? Now you should do that yourself, okay? And go ahead, start working on that, and I will start calling you very soon to see how you're doing. Oh, by the way, what do you have to know as well? You have to know the the resolution of your instrument, right? Whenever you're measuring a mass, in the case of the mass of the string, you are using a scale this experiment we're using scale is 5 decimal places. The Henke math had 5 decimal places as well. The length, total length of the string, we need that to find the linear mass density, which is lowercase m divided by L, is 3 decimal places. The vibrating length of the string you can measure as well. We measure that with the ruler or the meter stick, is 3 decimal places. And the wavelengths you measure also with the ruler, 3 decimal places. Those are the measurements that you take, and here are the decimal places that you have to worry that you must have there for your in your spreadsheet, for your data, right? For your raw data. So download the spreadsheet, plot graph, log the slope in the left table, from the units or kind of significant figures. Fill up the third table. Let's see what the third table is. Oh, that's the third table. After plotting the graph, you go to this table of results and always check the percentage difference. Don't forget to put the units, right? And then you work on the units, you work on the significant figures, and the last one you do is this one here. Okay? Make sure, okay, don't forget, when I was correcting this lab report, I was seeing groups that wrote down the CL, right? The confidence level was 1 minus 10 to minus 6, right? Notice that Excel doesn't recognize this value as a numeric value. It recognizes it only as a text. So I saw at least one group who did something like that. They forgot to put the equal sign here. Okay, when you put the equal sign, then Excel performs the calculation that you type. Make sure that you put that equal sign there, okay? Otherwise, you're going to lose points. You lose points with that. Want to wait. I'm going to give a few more minutes. And then I start calling. Where's the equal sign again? It's missed. Okay, whenever you are about to type the values of the CL, right? The minimum and maximum values of CL. Okay, you do the following. Type 1 minus 10 to whatever power you have to write, right? Let's say 10 to minus 7. Let's say. Okay, start that. If you do just that, you know, Excel is not going to do any mathematical. It's not going to process this equation that you wrote down. In order for Excel, why is that? Because Excel doesn't recognize this value that you see here, this cell that you have here, as a number. It recognizes it as a text. In order to ensure that Excel recognizes this value as a numeric value, you must put an equal sign here. So Excel will transform it as a number, as in an actual number. Okay, some groups forgot to put that equal sign and just left the value in there. Okay, make sense, Sardak? The equal sign goes to the left, right? goes to the left. And you do the same for the max, right? I also saw a group of students that they did the following. They didn't miss the equal sign, but they missed something else, okay? They, the minimum value, for instance, they put that 1 minus 10 to minus 5, right? And the maximum value, they put 1 minus 10 to minus 4. Okay? They swapped, right? This value here is less than this one. So this one is supposed to be in this cell, and this one is supposed to be in the other cell, okay? That's another group that made mistake. We do the cell values. Which error you get? Oh, yeah, this one is easy to fix, actually. This one is easy to fix, okay? Let me show you. I'm gonna put it here, right? Actual number. Okay? If what happens if the cell is shrunk too much, right? You didn't get there yet, right? Once you shrink the cell by too much, not this one, what a shame. Okay. But look at this cell. Look at the cell. See that? Well, what is happening here? It happens that the cell is too short, too narrow. You have to expand the cell to see the actual number there. Okay? That's how you fix that. Just by expanding the cell. Here you should get the same thing. Let's check. Let's see if you do it. Yeah, see that? Okay. Those one we didn't see that because I didn't format the number. You want to format the number as actual numbers with actual decimal places, right? Let's see. Yeah. It depends on the format. Depending on the format, you display the hashtag, and sometimes it doesn't. Okay. If I had noticed that I had what? I had a different format. I had a general format. This general format, it displays the number 1 here. Right? But if you put decimal places there, it is going to display the hashtag if the cell is not large enough. $115. I want to take a little break while you work there, okay? And it's going to be just about 5-10 minutes. And I'll be back soon. Please work on the spreadsheet. Okay, so let's see. Okay, before you folks, there's a group that finished already, right? So before you go, Alisa. Okay, that's group number 1, right? So what I want to know, what's your percentage difference, group 1, that you're getting?
It's like 13.1.
30%? Okay.
Oh, 13.714%.
Okay, good. Okay, so you already did everything, the spreadsheet, the graph, the units, and the significant figures, and the CL. You did everything?
Yeah.
Yep.
Okay. Okay, do you know what happened to my niece? She's not here today. Hello?
Yeah, we're not sure where she is, but we can reach out to her and see.
Okay. Okay, thank you. Okay, so you're done, you can go. What about Startup? Did you download the spreadsheet, Startup? Yeah. 0.038%. Okay. 0.038%. That's good. And you finished everything too. Number. Good. Okay, if you wanna go, you can go. What about Mary? Are you done, Mary? Yes? Okay. Okay, do you have any questions? No? Okay. What about Raymond? Raymond, what was your problem? You said something that you turn it on the Google Drive, but it keeps saying you on it still instead of me. I do not know. Let's see. Are you trying to upload the spreadsheet? Is that what you're trying to do, Raymond? Yes? Okay, so you're group number 2, right? The other students didn't have any problem, did they? The other students in group 2, Mary, and did you have are you having the same problem that Raymond is having? Hopefully they're still there. Mary and Sartak. Ah, you're turning for your group. Okay. Let's see what's going on here. It's not supposed to be doing that. Editor. Yeah, see? Are you sure? Let's see what there's in the scene. Yeah, I do not know why you're having this problem, Raymond. So you have the link and you are allowed to edit. Let me share the screen with you. See group number 2. Share. Anyone with the link just can edit. Okay, I'm gonna copy the link. I'm gonna send you the link again. See if it's a problem with the link that you have. Hopefully it will fix. You can also try to refresh the screen, right? Try to refresh the screen. And you said you're trying to put lab number 4 right in here. Okay, I see the Sartak put this document here. Okay, see that? Sartak put this document right in here. So he is capable of uploading documents. Yeah, that's right. So Sartak was able to upload the document. You should be able to upload as well. Let's take a look. Let's see, Raymond. Yeah, now you have it. Okay, so what was the problem? Do you know what was the problem? So it worked now, right? Refresh should be okay. You don't know. Maybe it was the title. I don't know. Those are some mysteries that we never figure out what it is, right? Mysteries of computers. Okay, and let's go for the next one here. Raymond is done. What about Basilio? How are you doing there, Basilio? Did you download the spreadsheet? Yes, that's good. Did you plot the graph? Yeah, okay. And what's the percentage difference you're getting? 0.1. Okay, pretty good. Pretty good. Are you done? Do you still haven't are you still working on something else? What are you doing? The next would be the units, right? You gotta take care of the units. Do you take care of the units already? I'm still working on it. Okay, good. And what about Joshua? Is he back? Hi, Joshua. Ah, okay, you're here. Good. So thank you. So do you download the spreadsheet, Joshua? Good. Plot. Did you plot the graph? Not yet? Okay, so working on that, right? Good. Zaid. Okay, let's move on to the next student. Zaid, are you there? Okay, did you plot? Did you download the spreadsheet, Zaid? Yeah, good. Did you plot the graph? Yes, good. Did you find the same percentage difference that Basilio found? Did you find the percentage? I'm working on that. Okay, good. So you gotta plot the graph, you gotta get the regression equation, and then you log in the slope in that table that provides you with the percentage difference. Now let's go to Karsika. Are you there, Karsika? Another chance to Kartika. Okay, I don't hear from Kartika. Let's go to the next, Sydney.
I'm here.
Okay, good. Did you download the spreadsheet?
Yes. And I'm on my laptop was like being weird, so I'm on mobile right now, so it's hard for me to see my graph, but can I get back to you on what my percentage error is when I like figure out my situation?
Okay, I'll put it working on the plot, right?
Yes, thank you.
Okay. Sumana? Yes, did you download it, right? Did you plot the graph as well?
Oh, yeah.
Yes? Okay. What about percentage difference you're getting? What's the percentage difference you're getting?
Pretty high. It's 4.64.
Can you type that for me in the chat box, please? You said 12.64? Oh, 4.6. Okay. 4.64. Okay, good. That's good enough. Did you finish the units in the spreadsheet? Yes? Okay. In addition to the units, you have the sig figs. Okay. What about the sig figs? Do you do the sig figs as well? Yeah. Next, after sig figs was that the CL, right? Did you do the CL already, or you're working on that? 1, 2, 3. Okay, so it looks like you're done, right?
Yeah.
Okay, so work with your group members, before you leave, and help them out with this data. And the next one I'm going to talk to is Kyriakos. Are you there, Kyriakos? Okay, good. Did you download the spreadsheet? I presume you did, right? Plot. You plot the graph. And what did you get the percentage difference? Straight. Okay, the same. Okay, good. Did you get the units? Did you work on the units? Did you finish the units, right? Yes. Okay. Sig figs. Sig figs. It looks like it's yes, right? No, don't know it's all. Okay, good. So help Sydney, and if you find Kartika there before you leave, okay, work together with Sydney before you leave. Let's go to group number 5. Andy. Is Andy there? one is done. And is not answering. Let's go for Alex Hernandez. Are you there, Alex? Oh, working on what? Help me figure out here what you're working on. So let me just ask, did you download the spreadsheet, Alex? Okay, good. Did you plot the graph? Yes. Okay, did you find the percentage difference? Not yet. Okay, so you're working on the percentage difference. Okay, just a matter of writing down the slope there in the graph. Okay, so you're still working. Let's see, Alexis, how are you doing there, Alexis?
Good. I did the plot. I did the sum of the units, and I'm working on the sig figs, and I still haven't done the CL or percent difference.
Okay, so you didn't do the percentage difference yet, right?
I see Andy's working on the percent difference. He just answered.
Okay. So, okay, I'm working on the percentage difference, but done with everything else. Okay, so let me, yes, working, yes, okay. Percentage difference, good, so 134. Is Kartika there? Kartika, I see Kartika handler here, but I don't hear from Kartika. Okay, we're gonna keep that as a star here. Group 1. Okay, well, let's see. Sartak, right? Can you hear me? Going back to Sartak. Okay, did you finish the unit, Sartak? Oh, we finished everything. Okay. Okay, do you have any questions? No? Okay. Before you go, let me check if your other group members are done or not. Mary, are you done? We're still working. Mary's not here. Okay, so I'm going to put the star here. And Raymond. I thought you were all done, right, Raymond? Or you done? Are you there, Raymond? Ah, finished with you. Okay, good. And what about Mary? What happened with Mary? Ah, she did too. Okay, good. Good to know. Basilio, okay, so if you're done, group number 2, you may go. Okay, and Basilio, are you there? Basilio, I can't hear from Basilio. It looks like Basilio left. Let's go here another one. Joshua, are you there, Joshua?
Yeah,
Okay, tell me what's your status there, what you have done so far. Did you plot the graph?
yeah, I completed plotting and the percent difference and the units now. I'm working on the sig figs and the confidence level.
And the percentage difference was the same as Basilio?
Yeah,
right?
yeah.
Okay, so finish unit and you're working on the sig fix. Good, thank you. And Daid. Are you there, Daid? I've finished the percentage difference. Okay, thank you. How much did you get for the percentage difference? The same. Okay, good. And now you're working on the. Are you working on the units? Did you finish the units? What's the situation here for the units? Oh, you finished the unit. Good. Sig fix. Done as well. Okay. What about CL? Done. Okay, so you've done everything. You're done with everything. So help Joshua. Okay, with his lab before you go. Karsika, one more opportunity for Karsika. Okay. Okay, so Sydney, how are you doing there? Did you plot the graph, Sydney?
Yeah, I did like earlier, and right now I'm still trying to get my like laptop working, but I plotted the graph, but I just can't see what that percentage error is. So I just need like 2 minutes if that's possible.
Okay, you're the one that are with your cell phone, right?
Yeah, I'm on my cell phone right now.
Okay. Yeah, it's
But
really
I'm like I got my laptop working and now I'm just like typing in Google Drive. So to like go back into it.
okay. Thank you. And now let's go to Alex Hernandez. Is Alex Hernandez there? Okay, Alex Hernandez is not answering. Let's go. Alexis Madrigal.
I think me and Andy are pretty much done with everything.
What's the percentage?
He says he's done with the percent difference now, so we're pretty much done.
And what's the percentage difference?
Hold on, let me check. Give me a second.
Around 8%. Right.
We got a value of 8.695. Some long number, but it's basically 8.695.
Okay, good. So I need, so you're done, right? Done. Sig fixed and done here as well. And Alex Hernandez, where are you, Alex?
This is Sydney, Professor, but I just wanted to let you know that I'm done as well.
Oh,
and the percent error was 4.636.
Okay, good. I like the audition. That's good. Okay, good. So Dawn, okay. Anybody else who is, this is Joshua, right? Still working on that. Okay, if you want to go, you can go. And 1:42 right now. You gotta figure out a way to make those labs more, how to say, challenging. Not difficult, but more challenging. I will stop recording now.